We all know GPS, right? I mean, it's everywhere these days. But can you imagine a time before that? Before our phones could tell us exactly where we are? Back when we had to rely on celestial navigation using the stars for guidance. Well, today we're diving deep into the patent that really laid the foundation for GPS. We're going to unpack Roger L. Easton's 1970 invention for a navigation system using satellites and passive ranging techniques. And this isn't just a history lesson. This is about understanding the ingenious solution to a problem that we all benefit from every single day.
You know, what's so fascinating about this is that Easton was addressing a big limitation of the early satellite navigation systems.
Okay, so before we jump into the specifics of Easton's solution, can you kind of paint a picture of those early systems and why was this passive approach so crucial?
Sure, imagine you're on a ship and you're trying to figure out where you are using a satellite. With these older systems, you'd have to send a signal up to the satellite and then it would send a signal back to you. But that back and forth could be intercepted, basically revealing your location to anyone who is listening in. Not good if you want to keep a low profile, especially in a military context. Plus, if you had multiple ships all sending signals at the same time, it could overload the satellite.
So Easton was thinking about a system where the navigator's device is only receiving signals, never transmitting, super discreet. But how do you figure out where you are just by listening? It sounds like magic.
It is a bit like magic, but it's the magic of physics and some very clever engineering. Easton's solution involved a network of satellites, each equipped with a super precise atomic clock. These satellites would constantly be broadcasting signals on multiple frequencies.
Hold on, atomic clocks in space. That sounds like science fiction.
It might sound futuristic, but atomic clocks were really a game changer for this system. They're these insanely stable timekeepers, and that stability is super important for the accuracy of the entire navigation system. But going back to those signals, the navigator's receiver, let's say on a ship, would pick up these signals and compare them to signals generated by its own highly stable oscillator, which would be synchronized with the satellite's clocks. And here's a really clever part. They used phase comparison.
Phase comparison. Can you break that down for me? I'm thinking like sound waves or something, but I don't really get how that translates to location.
Think of it like this. Imagine you've got two waves. One's coming from the satellite, and the other is generated locally by the receiver. If they start at the same time, but one arrives a little bit later, that wave had to travel further.
Yeah.
Like if you have two runners starting a race at the same time, and one crosses the finish line later, they had to run further. So that time difference is what we're measuring with phase comparison. And since we know how fast these signals travel at the speed of light, we can directly calculate the distance to that satellite.
Okay, that makes sense. So you're comparing the timing of the signals to figure out how far away the satellite is. But how does that tell us exactly where we are on Earth? I mean, one distance measurement doesn't give you a location.
Exactly. That's where the idea of triangulation comes in. So picture this. You draw a circle around the satellite, and the radius of that circle is the distance that we just calculated. So your position has to be somewhere on that circle. Now do the same thing with signals from at least two other satellites, and you end up with three circles that all intersect at one point. That point is your location. It's similar to how we use landmarks on a map to triangulate our position, but in this case, our landmarks are satellites.
So instead of using like mountains or lighthouses, we're using these satellites and phase comparisons to create those lines of position. That's brilliant. The patent also mentions using multiple frequencies. Why is that so important? Why not just use one frequency?
Well, that's another stroke of genius in Easton's design. The patent talks about using a range of frequencies all the way from 100 cycles per second to 100 kilocycles per second. And all of those frequencies are derived from a super stable 5 megacycle oscillator. And each frequency plays a very specific role. The lower frequencies give you unambiguous range measurements, meaning you know exactly how many wavelengths fit between you and the satellite. You can think of it like measuring a room with a yardstick. You can easily count how many yards fit across that room. The downside is the measurement isn't that precise.
So the lower frequencies give you a general idea of the distance, but not pinpoint accuracy.
Right. Now, the higher frequencies give you much greater accuracy. It's like using a ruler with really tiny markings instead of that yardstick. But because they're cycling so fast with these high frequencies, it's hard to keep track of exactly how many wavelengths fit between you and the satellite.
So it's a trade-off. You need both types of frequencies to get a complete picture. The lower frequencies give you unambiguous range, and the higher frequencies refine that measurement with pinpoint accuracy. It's like using a rough sketch to get the basic shapes right and then switching to a fine-tip pen for the details. I'm curious about how Easton actually envisioned all of this coming together hardware-wise. I mean, no fancy screens or computer interfaces back then, right?
No. The patent illustrations give us a glimpse into how the system was envisioned. They highlight key components like the stable oscillators and countdown circuits for generating the different frequencies, modulators for shaping the signals, and then a receiver and filter system to process those incoming signals from the satellites.
Okay, so paint me a picture. What would this have looked like on the navigator's end?
Imagine a device, maybe the size of a small suitcase with dials and gauges. Inside, you've got the stable oscillator just ticking away super precisely, and that oscillator feeds into these countdown circuits.
What are those circuits counting down exactly?
Well, think of them like tiny dividers, taking that high-frequency signal from the oscillator and breaking it down into all those different frequencies that Easton was talking about. 100 cycles per second, 300 cycles per second, 1 kilocycle, all the way up to 100 kilocycles. So those circuits generate the reference frequencies that are used for the phase comparisons.
Okay, so we've got our local clock generating those reference frequencies, but how do we actually receive the signals from the satellites?
That's where the antenna and receiver system come in. The antenna, maybe mounted on the deck of a ship, would pick up those faint signals coming from the satellites, and the receiver would amplify them and filter them, separating them from any noise or interference.
And then those cleaned up signals are sent to the phase meters. This is where we finally get to compare the timing of those satellite signals with our locally generated reference signals.
Exactly. And each phase meter is dedicated to a specific frequency. So for example, one phase meter might compare the 1 kilocycle signal from the satellite with the 1 kilocycle signal from our local oscillator.
And by measuring the phase difference between those two signals, we can calculate the distance to that particular satellite. So we've got these phase meters working away, each one giving us a distance measurement to a different satellite. And then by combining those measurements through triangulation, we can finally figure out where we are on Earth. It's just mind-blowing to think that this all started with a patent, and with Easton's vision for a passive ranging system.
And it wasn't just theoretical. Easton's work was the basis for timation. That's short for time navigation. Timation was like the precursor to the GPS we know today. Timation took these ideas and actually put them into practice, proving that they could work in the real world.
Speaking of timation, I'm really interested to learn more about how it bridged the gap between Easton's patent and the fully realized global positioning system. What were some of the key developments and challenges they faced in bringing this system to life?
I think that would be a great place to start in part 2 of our deep dive into the birth of GPS. I'm ready for that next chapter. The story of timation is full of incredible technological advancements and bumps along the road, and it all leads to the world-changing technology of GPS. So timation, it wasn't just a field test of Easton's concept. It was really a proving ground where they took these amazing ideas and had to figure out how to actually make them work in the real world.
Yeah, we've got this brilliant idea on paper, but what were some of those hurdles they had to overcome? I mean, launching satellites with atomic clocks, that technology was pretty new back then.
Oh yeah, the atomic clocks themselves were a huge challenge. They're these incredibly sensitive devices, and trying to get them to operate reliably in space with all the temperature extremes and radiation, that was a monumental task. They had to make some big leaps in materials science and engineering to create clocks that could withstand those conditions.
And I bet launching and maintaining an entire constellation of satellites was no walk in the park either.
Oh, absolutely. Timation needed a whole network of satellites all orbiting the Earth, and each one broadcasting these super precise time signals. So they had to master rocketry, orbital mechanics, satellite design. I mean, this was way before reusable rockets or miniaturized electronics. These satellites were much bigger and more complex than what we launch today, and keeping them up and running in orbit, that was a constant battle.
It really makes you appreciate how far we've come in space technology. But besides all the technical stuff, did Timation have to make any conceptual leaps to pave the way for GPS?
One of the biggest innovations that came out of Timation was this thing called pseudo-random noise coding, or PRN coding for short. It's this technique where they added a unique code to the signal from each satellite.
Okay, I'm curious, why add even more complexity to the signal? Wouldn't that make things harder to figure out?
It might seem counterintuitive, but PRN coding was really a breakthrough, because it allowed receivers on the ground to tell the difference between the signals from each satellite, even if they were all broadcasting on the same frequency. It's like giving each satellite its own unique fingerprint.
So it's kind of like having multiple conversations going on in the same room, but you can still follow each one because everyone has a different voice.
Exactly. And being able to separate those signals was key to achieving accurate triangulation with a larger constellation of satellites. Because if they were all sending out the same signal on the same frequency, the receiver would have no way of knowing which signal was coming from which satellite. So PR encoding really solved that problem.
Timation was like this breeding ground for innovation, pushing the limits of satellite navigation.
It really was a remarkable effort, and it's important to remember the historical context. This was happening during the Cold War, so there was a big military push behind all of this. The Navy saw the potential of this technology, being able to provide super accurate navigation for their ships, submarines, and aircraft. It would give them a strategic advantage.
That Cold War angle adds a whole other layer to the story.
Yeah.
Makes you appreciate the ingenuity and the dedication of everyone involved in this project. Ultimately, Timation proved that this global navigation system based on those principles could actually work. It wasn't just a pipe dream.
And that paved the way for GPS, the global positioning system that we all use today. GPS basically took everything that Timation pioneered, the atomic clocks, the phase comparison, the pure encoding, and scaled it up to a global level. It's really a testament to human ingenuity, building on those early breakthroughs to create a technology that's changed the world.
Yeah, it's incredible to think about that journey, from Easton's idea in that 1970 patent to the GPS systems we use every single day. But I'm curious about some of the ways GPS built on the foundation laid by Timation.
Yeah.
How did they scale things up and improve the system?
That's a great question. And that's where we see the evolution from a groundbreaking concept to a system that truly spans the entire globe. One of the key differences is just the sheer size of the satellite constellation. Timation had a limited number of satellites. GPS uses a much larger network with satellites positioned very strategically in orbit to provide coverage to the entire planet.
So more satellites mean better coverage and more accuracy.
Exactly. And GPS also brought in more sophisticated receiver technology. Those receivers used in Timation were pretty big and complex. GPS receivers have become smaller and more powerful because of all the advances in microelectronics. And this miniaturization has made it possible to put GPS receivers in everything: smartphones, cars, watches, even tiny tracking devices.
It really is amazing how GPS has become such a part of everyday life. But those early GPS receivers, even if they were smaller than the ones in Timation, they must still been pretty bulky compared to what we have in our phones now.
Oh yeah, definitely. The first GPS receivers were still really expensive and mainly used by the military and for specialized applications like surveying or navigating in remote areas. It took time for the technology to become affordable and for the general public to have access to it.
And that widespread adoption really led to all the innovative uses of GPS that we see today. Ride-sharing apps, precision agriculture, all sorts of things. GPS is now essential to so many industries and for so many people. But what about the accuracy of those early GPS systems? Were they as precise as what we have today?
That's another area where GPS has come a long way. Those early systems were groundbreaking for their time, but they weren't as accurate as the systems we have today. They could be thrown off by things like atmospheric distortion and limitations in the atomic clock technology at the time.
So how did they get more accurate over time? Was it just better clocks and more satellites?
It was a bunch of things working together. Those atomic clocks used in GPS satellites have gotten way more precise over the years thanks to tons of research and development. And the algorithms used to process those signals and calculate your position have gotten much more sophisticated. They take into account things like the curvature of the Earth, the movement of those satellites, and even those relativistic effects.
Relativistic effects.
Right.
Like Einstein's theory of relativity. That's wild.
It is. Because those GPS satellites are moving at such high speeds and in a different gravitational field than the receivers down here on Earth, we have to account for those relativistic effects to get the incredible accuracy that GPS is known for.
It's like this crazy symphony of physics and engineering all working together. But I'm sure even with all those advancements, there are still some limitations to GPS technology. I mean, we all know that those GPS signals can be a bit iffy sometimes, especially in cities with tall buildings or out in the woods.
You're right, GPS is incredible, but it does have its limits. The signals from those satellites are pretty weak. They can get blocked or messed up by buildings, trees, mountains, even the weather.
Yeah.
That can lead to less accurate readings or even a complete loss of signal.
So it's not a perfect system, but it's still pretty amazing that we can figure out where we are on this giant planet using signals from satellites thousands of miles away.
It really is. It's a testament to how clever humans can be and the power of scientific discoveries. And it doesn't stop there. GPS tech is still evolving with new research and development happening all the time to improve the accuracy, the reliability, and make it even better.
Sounds like there's a lot more to explore in terms of the future of GPS and all those cool applications coming out. But before we get into that, I have one more question. We've been talking about the technical challenges with Chimation and GPS, but what about the human side of all of this? What are some of those personal stories and those aha moments that really shaped the way this technology developed?
Yeah, that's a fascinating side that often gets overlooked. Behind all this complicated equations and engineering feats are real people with their passions, their struggles, and their moments of inspiration. And one story that comes to mind is the story of Roger Easton, the inventor whose patent we talked about earlier.
Oh yeah, he was a true visionary. He saw the potential of this tech before many others did. I'd love to hear more about his journey and how he helped to make GPS a reality.
His story is a really inspiring one. Easton was a physicist and engineer who worked for the U.S. Naval Research Laboratory. He wasn't even working on navigation originally. He was working on this system to track satellites. But then he had this aha moment, and he realized if you could track satellites from the ground, then maybe you could also use them to figure out where you are on Earth.
It's those sparks of insight, those connections that link up these seemingly random ideas that often lead to those big breakthroughs. And in Easton's case, it led to a technology that's changed how we live.
And there are so many other stories like his. Stories about all the scientists, the engineers, the mathematicians who dedicated their careers to making this tech a reality. They faced setbacks, technical roadblocks, even skepticism from people who didn't believe it could ever work. But they didn't give up. They were driven by this vision of a world where anyone could have access to super accurate navigation.
Yeah. These stories remind us that innovation isn't just about equations and circuits. It's about human passion and creativity and this never-ending desire to create a better future.
It really is. And as GPS keeps evolving, it's important to remember the human stories behind it. The stories that show us that anything's possible when you mix ingenuity with determination.
It feels like we've just scratched the surface of this amazing story. From celestial navigation to atomic clocks, from the Cold War to the era of smartphones. GPS has come such a long way. And as we journey into the unknown of the future, one thing is for sure. GPS will keep on playing a big role in shaping our world.
There's so much more to discover. And in the last part of our deep dive, we'll take a closer look at the lasting impact of GPS. We'll explore how it's changed society, the challenges that still remain, and the exciting possibilities ahead.
So you've seen how GPS evolved from this kind of like futuristic idea in a patent to this global system that we all use to get around. But the story doesn't stop there, right? GPS is more than just tech. It's like this force that's changed industries and empowered people. And it even raises these big questions about things like privacy and security.
Yeah, it's become so ingrained in our lives that it's easy to forget how much of an impact it's had. I mean, think about it. We use GPS for everything, from navigating traffic to tracking packages to even coordinating emergency response and keeping tabs on environmental changes. It's hard to picture what the world would be like without it.
It's almost like a utility at this point, like electricity or water. We just expect it to be there, and we don't really think about how complex it is or how it even works.
Right, and that's led to a boom in innovation. People are using GPS in ways that those early pioneers like Easton could never have imagined. Like precision agriculture. They use GPS to guide farm equipment and figure out the best ways to plant and fertilize and even monitor crop health. It's helping farmers grow more food and be more environmentally friendly at the same time.
It's pretty amazing to see how GPS is being used to tackle some of the biggest challenges in the world, like food security and climate change. But I'm also thinking about the flip side of that. You know, that same tech that enables all this good stuff could also be used for surveillance and tracking. That raises concerns about privacy and the possibility of it being misused.
That's a really important point. Like any powerful tool, GPS has two sides. It can be used for good or bad. Being able to pinpoint someone's location so precisely raises some ethical questions about surveillance and data privacy. And it's about trying to find that balance between security and individual freedom.
Yeah, it's a complicated issue. We want to have all the benefits of GPS, but we also want to protect our privacy and make sure it's not being used for the wrong reasons.
Finding that sweet spot is tough. We need to be having open discussions about the ethical implications of GPS and put in place safeguards to stop people from misusing it. Things like strong data privacy rules, transparency about how data is collected, and ways to hold people accountable.
It's a reminder that tech innovation shouldn't happen in a bubble. We have to consider the social, ethical, and legal aspects too, not just the technical stuff.
Exactly. And as GPS tech keeps getting better and better, these conversations become even more critical. We're seeing these new and super accurate positioning systems popping up, like Galileo in Europe and Beidou in China. And with self-driving cars and all those location-based apps, the need for GPS is only going to grow.
So the stakes are getting higher. But with all this complexity and all these challenges, it's important to just pause and acknowledge how amazing this technology actually is. The fact that we can pinpoint our location on a planet that's zipping through space, using signals from satellites orbiting thousands of miles above us, that's just incredible.
It really speaks to human ingenuity and our constant desire to understand the world around us. From looking to the stars to figure out where we are, to the invention of atomic clocks, from the Cold War to the age of the smartphone, GPS has come a long way. And as we move into the future, one thing's for certain. GPS will be a huge part of shaping that future.
And who knows what mind-blowing possibilities are still out there. Maybe someday we'll be using GPS to travel not just here on Earth, but to other planets in the solar system, even beyond that.
That's something for our listeners to think about. From the stars to our phones, the journey to understand where we fit in the universe continues.
This has been another deep dive, and we'll be back soon with another fascinating piece of history that has shaped the world.